Hello again. Today we will learn how to construct truth tables for arguments. This is what we've all been waiting for since we started the second section of our class, the section on propositional logic. We've been working up to being able to do truth tables for arguments. So using truth tables, we can determine the validity of arguments. Now I have a test for you. What is it for an argument to be valid? A, if its premises are true, the conclusion is probably true. B, if its premises are true, the conclusion must be true. Or C, its premises are in fact true and the conclusion is in fact true. The answer is B. Take a second, pause the video, see if you can explain your answer to yourself. Okay, so why is it B? Well, let me start with A. It's not A. That's the definition for an inductively strong argument. That has to do with induction and strength. When the premises are true, the conclusion is probably true. Like if you had a die and on 4 faces of the die it had the number 1, or had 1 dot, and on the other 2 it had 2. So 2 on one face, 2 on another face, and then 4 faces with 1. Well, what you would say is, if I roll this die, it is probably going to land on 1, although there's a chance that it could land on 2. That's kind of like induction. You have it gives you a probability, not certainty. When it comes to deduction, you get certainty. So suppose you had a die instead with 1 on all 6 faces. Now, unless it lands on the corner or something, if it lands on one of its faces, it's going to be the number 1. It's a guarantee. So that's just like deduction. If the premises are true, the conclusion has to be true. It's impossible for it to be false. And it's not C. All that C says is the premises are true and the conclusion is true. It doesn't say what must be the case. It doesn't say that it's impossible for the conclusion to be false. It just says the premises are true and the conclusion is true. So for example, like if someone says the sky is blue, well, that would be true, depending on the time of day, I guess, or if it's not night or if it's not sunset. But notice that it doesn't have to be true for the sky to be blue. It just happens to be true right now. For it it must be true for the sky to be blue. That means that it's actually impossible for the sky to be anything other than blue. Okay? So that's what distinguishes C from B. C just says what actually is the case. B says what must be the case. So when you come to validity, we're saying that if the premises are true, then the conclusion absolutely must be true. And the reason that's the case is because the premises, from the premises, the conclusion follows with certainty. All men are mortal. Socrates is a man. Therefore, Socrates is mortal. If all men are mortal, if that's true, if Socrates is a man, if that's true, then the conclusion must follow that Socrates is mortal. That's a deductively valid argument. Now let's do a truth table for an argument to try to determine whether it's valid or invalid. Okay. Well, but first, though, we need to ask, how do we know that an argument is valid just because none of the lines in its truth table have true premises and a false conclusion? You need a little background for this. So the way that you determine for a truth table, for an argument, whether the argument is valid or invalid, is you look for a line in which the first premise comes out true, the second premise comes out true, and the conclusion comes out false. If you cannot find such a line where the premises come out true and the conclusion comes out false, then the argument is valid. If you can find such a line where the premises come out true and the conclusion comes out false, then the argument is invalid. Why is this? Well, first, we're listing all the possible combinations of truth values for the component statements, and so that means we're listing all the combinations for the premises and the conclusion. You know, the premises might be true and the conclusion is true. Premises might be false and the conclusion is false. One premise might be true, the second premise might be false, the conclusion might be false. We're listing all the possible combinations, every single possible combination. If no lines come up with true premises and a false conclusion, you know that such a line isn't possible because you've listed all the possibilities. If no lines come up with true premise, false conclusion, you know that such a line isn't possible. If it's not possible, then you've shown that for this argument, it's impossible for the premises to be true and for the conclusion to be false. Namely, you've shown that it's valid. If you find a line where you have a true premise, false conclusion, you've shown that it's possible for the premises to be true and for the conclusion to be false. Namely, you've shown that the argument is invalid. I think it'll be helpful to get an example so that you can see what I mean. Suppose we have the following argument. It's not the case that both John is going and Rita is going to the party. That's premise 1. Premise 2, John is going. Conclusion, therefore Rita is going. So how do we determine if this is valid? I mean, you might look at it and say, well, obviously it's not valid. It says they're not both going, and then it says they're both going, right? But let's just, do the truth table on this argument to show that it's invalid. So how do we determine if it's valid or invalid? Well, first just symbolize it. We'll let P equals John equal John is going and Q equal Rita is going. So now we have the following argument. Premise 1, tilde P dot Q. Premise 2, P, therefore, conclusion Q. That's our argument. Now we need to do a truth table on it, and I'll show you how to do that. So, here's the argument. We need to construct a truth table for it. The steps for constructing a truth table for an argument. First, you set up the truth table and you identify the conclusion with a forward slash, placing the component statements in the top left column, right here, right? Because look through this argument. This is premise 1, this is premise 2, this is the conclusion. Find all the component statements. We just have P and Q. And then P and then Q. So we list all the component statements in the top left column, P, Q. And we do P first because it appears first in the argument. We do Q second because it appears after P. So P first, Q second. So we place the component statements in the top left column right here. And then the first premise in the column after that. That's what we did. Premise 1. The second premise in the column after that, right here. And then the conclusion, which we mark as the conclusion with the forward slash. This is, let's say it symbolizes the word therefore. We put the conclusion in the last column. So that's how you fill out the top portion of your table when you're doing a truth table for an argument. Then you fill out the bottom left column right here. And we've seen that when you only have 2 component statements, that means you have 4 possible combinations, and you do TT, TF, FT, FF, where you start with T in this column and you alternate by 1s, TF, TF, and then you start with T in this column and you alternate by 2s, TT, FF. That gives you all the possible combinations. All right, so far, nothing much is new except for you list the premise 1 first, premise 2 second, and then the conclusion. And you might have like 4 or 5 premises, so you just keep listing all the premises in order, and you mark the conclusion off by the forward slash. So what's next? You fill out the truth table according to the order of operations in box each main operator. So that's what we did here. Filled out the truth table according to the order of operations. So we start with we start by filling out the column that has the least in its range. So that would be the dot. It just ranges over the P and the Q. And then we did the column that has the most range, that would be the tilde, because it ranges over this whole thing. And so we filled out that column, and we boxed it. Okay. And then for these, there is no operator, so you just list the truth values for P, list the truth values for Q, and box each one. Even though it's not an operator, you should still box it. The reason you box it, the thing that you're boxing gives you all the possible truth values for that premise or that conclusion. Okay, so how did we do TFFF? Well, it's a conjunction. So when P is true and Q is true, the conjunction comes out true. When P is true and Q is false, the conjunction comes out false. When P is false and Q is true, the conjunction comes out false. When P is false and Q is false, the conjunction comes out false. And then, how do we figure out this tilde? Well, it's a negation of a conjunction. A negation of a conjunction. Remember that when you come to a negation, the truth value for the negation is the opposite of the truth value of the thing it's negating. So, when the conjunction is true, a negation of the conjunction is false. When the conjunction is false, a negation of the conjunction is true, and so on. So, since this is the main operator, we box it, right? And then we have P. Well, what are the possible truth values for P in combination with the premises and the conclusion? You just list the truth values for this column, and you list it over here. True, true, false, false. And then for Q is the same thing. True, false, as you see here. Okay, so now we've filled out our entire truth table. Now we need to determine whether it's valid or invalid. With step 4, we see that we check for lines with true premises and a false conclusion. If no such lines exist, the argument is valid. If such a line exists, the argument is invalid. Okay, so the truth value for not P and Q on this line, number 1, is false. The truth value for P on line number 1 is true. Truth value for Q on number 1 is true. We don't have true premises and a false conclusion. We have a false premise, a true premise, and a true conclusion. For line 2, the truth value for not the case that P and Q ends up being true. For the second premise, the truth value is true. For the conclusion, it's false. So we have true premises and a false conclusion. Okay, so that is our line that shows it's invalid. But let's keep going, and then we'll move on to step 6. Step 5. There is no step 6. For the third line, the truth value for not the case that P and Q is true, because the truth value is determined by the main operator. For the third line, second premise, it's false. For the conclusion, third line, it's true. So we don't have true, true, false. And then for the fourth line, we have true, false, false. So the only line, which is all we need, but the only line where the premises come out true and the conclusion comes out false is the second line. Okay, so we did step 4, we checked for lines with true premises and a false conclusion. If no such lines exist, the argument is valid. If such a line exists, the argument is invalid. Such a line exists. So for step 5, if an argument is invalid, place a check mark on the line that has true premises and a false conclusion. Check. Line 2 has true premises, true, true, and a false conclusion, false. And you write invalid to the side, invalid. And if you want, you could put the exclamation point, It's, invalid. All right. If it's valid, you don't put the check mark and you simply write valid to the side. Okay. How does this show that the argument is invalid? We have premise 1, premise 2, conclusion. Remember, with a valid argument, it's impossible for the premises to be true and the conclusion to be false. So if no lines on the truth table exist where the premises are true and the conclusion is false, you know that it's valid because you've seen that it's impossible for the premises to be true and the conclusion to be false, because you've listed every single possible combination of truth values to the premises and the conclusion. All the possible combinations. If it's valid and there aren't any lines where there are true premises and a false conclusion, well then you know it's impossible for the premises to be true and the conclusion to be false. When it comes to this argument here, you've shown that it's invalid. You have true premises and a false conclusion. Why does this show that it's invalid? Well, think of the definition of invalidity. It's possible for the premises to be true and the conclusion to be false. It's possible for the premises to be true and the conclusion to be false. Well, we listed all the possibilities of truth values for the premises, truth value combinations for the premises and the conclusion. There are 4 possibilities. Premise 1 is false. Premise 2 is false, true. Conclusion is true. Premise 1 is true. Premise 2 is true. Conclusion is false. Premise 1 is true. Premise 2 is false. Conclusion is true. Premise 1 is true. Premise 2 is false. Conclusion is false. Those 4 possibilities are the only possible combinations of truth values for the premises and the conclusion. Since we found that it's possible for the premises to be true and the conclusion to be false, boom, we've shown that it's invalid. Alright, before I end, I want to emphasize the importance of this process. When you do a truth table for an argument, you're trying to determine whether the argument is valid or invalid. You're trying to determine whether the argument is valid or invalid. If you do the truth table and you don't find a line where you have true premises and a false conclusion, you've shown that the argument's valid because you've shown that it's impossible for the premises to be true and the conclusion to be false. But that's just the definition of validity. If you do your truth table and you show that there is at least one line where the premises are true and the conclusion is false, you've shown that it's invalid. Because that's just the definition of validity, that it's invalidity, that it's possible for the premises to be true and the conclusion to be false. All right. I think I've said it, and with passion. So I hope you understand it. If not, please let me know. This is super important. You're not going to do well on the test if you don't understand this. Okay. Have a great day.